Hello guys, let's continue our discussion on shear strength. So I stopped somewhere here before I started the shear span. So I will now be giving you some uh, lecture on shear span concepts. So what is a shear span? Okay, a shear span is a variable that actually is used to categorize, okay, or to characterize your beam as to its dominance in shear or flexure. Okay, so a beam may be a dominant, or when you say dominant, it's critical in flexure or critical in shear, depending upon the shear span variable that we are going to study uh, here in this presentation. Okay, and this is actually given by the variable a. So a is actually what you call the shear span. So if I have here a beam which is simply supported, so sorry for the drawing, this must have a support here, a reaction here. Okay, so my shear and moment diagram will simply look like this. Okay, so it will be your reaction here will be V, and your reaction here will also be V. So that summation forces vertical will be equal. Okay, 2V is equal to 2V. Of course, this will go up V, and then it will go down by V there. And then no load, 0. Then it will go down again by the V force there, negative V, and a negative V, and then it goes up there. Okay, so this is now my shear diagram. Very simple shear diagram. And of course, the moment can now be computed on the basis of the area. So what's the area of this figure here? So you can get now the moment there by area method. So this is simply A times V. So the moment here is A times B, and the moment also here is A times B. Of course, this constitutes a no change in moment, and then if I subtract a negative, this is a positive A times B, it is a negative A times B. If I subtract AB minus AB, it becomes a 0 here. Okay, so this is my moment diagram. Okay, so let me get my charger first. Okay, so to continue now, how do we use now the shear span variable to categorize or characterize a beam in terms of dominance? Okay, so I want you to take note of the word dominance here. So let's first define what's the formula for shear. Okay, so this is now your shear for shear stress, small v. Okay, so this is the shear stress, which is a function of the shear force divided by BD. Okay, it's simply a force all over an area multiplied by a certain coefficient, we don't know, K1. And then we also know that F, your flexural stress, as we note on your elastic concepts in flexure, is simply a moment all over a certain parameter. You call this the section modulus. Okay, okay, multiplied by, again, another coefficient k2. We don't know what's the value. But what is important there is if we divide F divided by V, we get this formula. And so, looking into the K1, K2, which we try to neglect because we are just looking into the concept of getting a value so as to categorize, no? We're not after the exact value, so we just want to have an indication of which is more dominant. So we simply divide F and V, ignoring your case there. And notice that this will just simply cancel out. Okay. So your BD squared here, your BD there will cancel, your BD will cancel. So your formula now, F over V, will simply be M over V times 1D here. So you still have a D here because this is squared. So this is now your ratio. Okay. So this is just a ratio of F over V. And if you're going to look at if we're going to include now the concept of shear span inside this formula, we simply let your A be the ratio of this M over V, such that if we are going to simplify this, we can come up with F over V is simply A over D. Okay? So this is now your simple uh, relationship, okay, that will give you an indication whether uh, your flexure is dominant or critical rather than your shear. And how do we do that? Now, take note that the large value of F over V or A over D will imply dominance in flexure. Why? Because if F over V is big, then the moment is bigger than V. Okay, so that's the rationale. Okay, uh, that is the scientific explanation of having a dominant flexure when your A over D or your F over V is large. Of course, if it is small, there's dominance in shear. So to look into now a more precise relationship on how to characterize a beam in terms of the A over D ratio. So you now call this your shear to span, sorry, shear span rather to depth ratio. Okay, so means say we are dividing A over D, then just remember these values. Okay, so A over D greater than 6, the beam is long. A over D is in between 2.5 and 6, the beam is intermediate. A over D is less than, it's A over D is in between 1 and 2.5, it's short. And A over D is less than or equal to 1, it's deep. Okay? Okay, so this is now our guide to categorize what type of beam are you analyzing in terms of the A over D ratio. Okay, so what is a long beam, intermediate beam, short beam, and deep beam? So we are now on the context of trying to understand the failure pattern or mode of these different types of beams. So for long beams, failure is governed by flexure. Okay, because what? Because this is giving you a dominance, implies a dominance in flexure, therefore it will fail in flexure, or critical. If you don't want to use the word dominance, it's critical in flexure. And the flexure shear crux actually is the point of observation, because this is more likely to form. Okay, remember the crack pattern that I discussed a while ago. And then also, your ultimate strength entirely depends on the moment values. So in short, class, when you are looking into a long beam, all is actually focused on the flexural behavior. Okay, for intermediate beams, uh, I'd like to skip this, no? Let's go to the short beams first and then try to understand what is intermediate. So for short beams, ultimate shear capacity exceeds the inclined cracking load. So meaning to say, the capacity of your concrete to handle the shear force is already exceeded, and therefore your beam will crack in a diagonal manner. Okay, so inclined means diagonal. Okay, crushing of uncracked concrete after occurrence of diagonal crack is likely to happen. So remember the shear mechanism. Number one, the VZ, no? Okay, so this is the VZ that we are talking about a while ago. So your VZ is actually uh, also exceeded, such that after the cracking, your beam will ultimately fail. And then for letter C, there will be now a loss of band stress on the tension side of the beam. This is actually a secondary effect, or a secondary uh, failure that is attributed to the secondary cracks that we ought to understand later. Okay, so after your long and short, we can now go into the middle of this, which is the intermediate beam, wherein the sudden occurrence of inclined crack will still be a part of your flexural crack. Still, no? Still very much the same, but there's already your diagonal crack here, meaning to say it's now a combination of flexure and shear. Okay, and it fails shortly after the application of diagonal cracking loads, and the crack propagate over a depth of the member. So your intermediate beam simply behaves like a shear flexural behavior. Okay, so if this behaves in flexure, this behaves in diagonal shear. Okay, this will behave at the middle, shear flexural. Okay, again, for deep beams, we will be dealing with this separately, because the codes gives us other guidelines on this. But still, I'd like you to remember, for deep beams, it is just like an arc, tide arc, that is behaving differently from a normal beam. Okay, and it sustains a considerable amount of load above the inclined cracking load. So imagine you have a very deep beam here. Okay, just like a wall, almost you can see it here, a wall, wherein there's an arc action. Okay, an arc action like this. Okay, so this serves as a tide arc, which is tied by the reinforcement at the middle. So it actually is a very strong beam, but the failure is more likely to have on the shear aspect rather than the flexural aspect because it's deep. But it's beyond, sabi ko nga, it's beyond the code uh, guideline for ordinary beams, so it is actually separately discussed in the code because of some formations of cracks which are not a part of the shear flexural crack behavior that we are talking about. Okay. Now, for the determination of your VC, we now look into the formula. So what's against your VC? VC is the contribution of VZ plus VA plus V dowel. Okay. So remember, this is the mechanism for VZ. And unfortunately, the determination is not purely analytical. It's a semi-empirical, meaning to say it is actually on the basis of experiments. Okay, wherein the load causing formation of the critical diagonal tension crack considered as load carrying capacity of the beam BC is just based on this form. This is still your elastic uh, concept on shear, and eventually converted into a inelastic concept in the form of this formula. Okay, so I don't want you to look into this formula because this is based on experimental study, but just like you to look into the variable concerned. This is the square root of fc prime, m over vd, and rho. Okay, so I just want you to pick these three variables because these are the important variables to consider on your formula. Okay. Okay, and these are the factors actually which affects your VC. No, so we have the rho or the rho W. The W there simply states that this is based on the width of the web in case it's not a rectangular beam. Okay, rho and rho W are just equal. So your M over VD, which is actually your A over D, again, what's this? This is, of course, this is simply your rho if rectangular and rho W if it's a T-beam. Okay, if it's a T or an I beam, it's a rho W. So for your M over VD or A over D, this is the shear span to depth ratio. And for your square root of fc prime, this is the measure of your tensile strength. Remember your modulus of rupture? Okay, it's the square root of fc prime times 0.62. Okay, so this equation here, class, by the way, is a graph is actually represented by this graph here. Okay, so you just look into this graph, and if you will look at this plot, it will now be converted into a solid bilinear plot, which is this one here. Okay, so we will not derive it because this is experimental. This is the one that we are going to use in our formula because this is SI, but in case we'll be using English units, so we will be using this formula. So I hope you can remember this formula. And there's a limiting value here, which is 0.30 square root of FC prime BWD, which is, this is your English unit. Okay. So the equivalent of this for your SI is 0.30. Okay. No? So take note that V do D over MU. Now we have a subscript U to give you a conclusion that we are using now your factored shear, and the factored moment must be less than or equal to 1.0. It cannot be greater than 1.0. So for everyday design, this can be simplified further. We will try to compare this, and because this is SI and this one. Okay, so mamaya compare natin to. When you say everyday design, this is the simple formula. This is the detailed formula. Okay, so this is the detailed. This is the simple formula. Okay, so I'd like to stop here to entertain again your questions. So after this video, I'm going to present an example of some characterization or categorization problem regarding shear span to depth ratio on the next video. Okay, so thank you.